Yes, let us discuss BH2 molecule. Central atom is beryllium. Electronic configuration 1s2, 2s2. 4 electrons only are there in beryllium. And remaining atoms, remaining hydrogens, peripheral atoms, they will form a group. How the group orbitals are there, how interaction is there, let us see. In order to understand the various molecular orbitals formation for BH2 molecule, you need to know its point group. Its point group is D infinity H. What does it signify? There is C infinity axis, and it's true. Along hydrogen, beryllium, hydrogen, passing through both bonds, there is a C infinity axis. There are C2 axes. There are improper axes of rotations. There are vertical planes. But most important operations for us are inversion and reflection through horizontal plane. If you have to understand clear-cut formation of various molecular orbitals, then first step you need to follow understanding symmetries and energies of outermost orbitals of central atom. Which is central atom here? Beryllium. So 2s and 2p orbitals, their orientations, their energies, symmetries, the labeling for them that we need to understand. Second step about the group orbitals. Peripheral hydrogens are there. How do they combine? Which group orbitals are obtained? Which orbitals are suitable? That you need to digest. And last important point is interaction between group orbitals and suitable atomic orbitals of central atom. Here is beryllium in order to produce molecular orbitals. Let us see what are the energies of various orbitals. We are with beryllium as a central atom and it has electrons in second shell. So only two orbitals are there, 2s and 2p. Energy of 2s orbital of beryllium is minus 9.3 electron volt. And for 2p orbital, exact data is not available with me, but it is near about minus 2 to minus 3 electron volt. While energy of oneness orbital of hydrogen, those oneness orbitals are going to establish group orbitals. Their energies are minus 13.6 electron volt. So lowest energy orbitals are hydrogen orbitals. Afterwards 2s orbital of beryllium, then 2p orbital of beryllium. But energy gap between highest orbitals present on beryllium means 2p orbitals and group orbitals of hydrogen is within the range. Those can interact to produce various molecular orbitals. So we need to consider if symmetry permits, interaction will be there. So let us see what is the role of symmetry, how the group orbitals are resulted. Each of these peripheral hydrogen atoms has one electron in oneness orbital, and that electron in oneness orbital will behave like a wave, and wave of one hydrogen atom A will interact with wave of other hydrogen atom B, but they are forming group. Ultimate molecular orbital will be produced after interaction with orbitals of central atom. But this wave will group in how many ways? Let us see. It seems that these four ways are there for the combination of group orbitals. But in true sense, from mathematical way, only two types of combinations are there. How? That I explain. Before that, let me describe this diagram. By dark color, I am representing positive waves. So by dark purple color, hydrogen A, that's a wave of atom A is represented, positive wave. Dark red color, positive wave of atom B is represented. And by faint colors, negative waves are represented. If you see, the two compartments are made. In the left compartment, positive wave of atom A groups with positive wave of atom B, and in second half negative wave of atom A interacts with negative wave of atom B. If I have to conclude the interaction is like kind. Like interacts with like. Positive interacts with positive. Negative interacts with negative. Same phases interact with each other. That is a left compartment. And a right compartment, positive wave of atom A interacts with negative wave of atom B. And second part, negative wave of atom A interacts with positive wave of atom B. So what kind of combination it is? Unlike a kind of combination. Positive interacts with negative or negative interacts with positive. It is a second type of the interaction. Mathematically, how can I describe these two interactions? Left compartment group can be represented as psi1. It is the first group. Psi1 Gr is equal to psi1s for hydrogen A, means wave function for hydrogen atom A, plus. Why plus sign? Because in left compartment, in first possibility, both atoms have same wave function. Addition will be there. Therefore, plus psi1s. It is for which atom? Hydrogen B. Similarly, right compartment interaction of group orbitals can be represented as psi2, means second wave function of group orbitals. Psi2 Gr is equal to psi1s. It is for hydrogen atom A, minus. Why minus sign? Because unlike signs are there, different signs are there, different wave functions are there for grouping orbitals A and B. Means if one is positive, other will be negative and vice versa. Therefore, psi1s for hydrogen atom A minus psi1s for hydrogen atom B. What is psi? It is a wave function. See the symmetry of left compartment group orbitals. We are talking about linear BeH2 molecule. So what is the point group for that? D infinity H. So possible operations are C infinity, C2 axis are there, horizontal plane, center of inversion. Now I want to bring your attention more towards the horizontal plane or center of inversion. Because out of those two, any one is sufficient for us to distinguish these two kinds of the groups. Left compartment group is symmetric about horizontal plane or center of inversion, while right compartment group is unsymmetric or non-symmetric about center of inversion or horizontal plane. So also it is called psi1 group as a symmetric and psi2 group as non-symmetric. Here, or symmetry with reference to horizontal plane or center of inversion. Those are the possible operations for D infinity H point group. So in conclusion, two kinds of possibilities are there to group peripheral hydrogen atoms wave functions. Let us know the orbitals from beryllium and their symmetries. Lowest energy orbital is 2s orbital. It is spherically symmetric. Wave function can be either completely positive or completely negative. Let I take any operation possible for d infinity h point group. 2s orbital will be symmetry. Therefore, I said there it is symmetric with respect to all operations of d infinity h point group. Do you remember which group orbital was there which has such symmetry? Yes, that's a psi1 group. So now you might be getting the point. 2s orbital is eligible to combine with whom? Psi1 group from peripheral hydrogens. Now come to the next orbital. That's a 2px. It is along the two bonds. Beryllium hydride has two bonds, hydrogen, beryllium, beryllium, hydrogen. So along that our x-axis is there. So this px orbital is symmetric about many of the operations, but it is not symmetric with respect to horizontal plane because left side positive phase, right side negative phase is there. Let you consider center of inversion also, but for the sake of simplicity I am considering only horizontal plane. So it is non-symmetric or not symmetric with respect to horizontal plane. So for distinguishing purpose, this one point of horizontal plane is sufficient. If I come across other orbitals, 2py and 2pz, interestingly, they are not symmetric about principal axis. That's the C infinity because they are not along the bond. They are not along the C-infinity axis. They are perpendicular to the C-infinity axis. Therefore, I said there 2py and 2pz are not symmetric with respect to C-infinity. But such orbitals were not from the group of hydrogens. Therefore, we need to think about these 2py and 2pz with whom they can combine. Let me know what about 2px, which orbital, which group orbital is suitable for interact? Yes, Psi2 group orbital, which was not symmetric with respect to horizontal plane, is suitable for 2px. So now it is sure now. 2s orbital can interact with Psi1 group, 2px orbital can interact with Psi2 group, 2py and 2pz are with no any partner, no any suitable orbitals to interact or overlap. Is the application of symmetry to the atomic orbitals of beryllium and group orbitals of hydrogen clear? Let us recap regarding 2 points. Energy, which orbitals are suitable to interact? Yes, 2s and 2p both orbitals are suitable to interact with group orbitals of hydrogen. Energy gaps are sufficiently low, which was one of the essential conditions to form molecular orbitals. Second point is about symmetry. Symmetry discussions regarding atomic orbitals of beryllium and group orbitals caused by peripheral hydrogens. 2s orbital of beryllium is suitable to interact with which group orbital? Right, psi1. And what about 2px orbital? Suitable to interact with psi2 group. 2py and 2pz orbitals have no suitable symmetry other orbital, therefore they may remain non-bonding. Let us see the molecular orbital diagram for BeH2 molecule. In this MO diagram, 1s orbital of beryllium is not represented. It is an inner orbital and which is not involved in the formation of molecular orbital. So it will remain non-bonding. More focus is given for 2s and 2p orbitals of beryllium and their interaction with group orbitals of hydrogen. Left side atomic orbitals of beryllium. Middle portion of the MO diagram includes molecular orbitals of molecule BeH2 and right side two group orbitals of two peripheral hydrogens. Beryllium has only 2 electrons in the 2s orbital. Now how interaction is going to occur? 2s orbital of beryllium interacts with psi1 to produce two molecular orbitals. One is bonding and one is anti-bonding. One is 2 sigma orbital and other is 4 sigma star anti-bonding orbital. Similarly, 2px orbital from beryllium will interact with psi2 group orbital to produce two molecular orbitals. Which are those? 3 sigma as a bonding orbital and 5 sigma star as anti-bonding molecular orbital. Now left two orbitals. Which are those? 2py and 2pz on beryllium. They are with no suitable partner to interact, so they will remain as it is. Their energy will not change, as was the case for as was the case for 1s orbital of beryllium. Same will be the case for 2py and 2pz orbitals, but those are outer orbitals. Now see the labeling. 1s orbital of beryllium has sigma symmetry, so label will be 1 sigma. Afterwards, bonding orbital is there caused by 2s orbital and psi1 group, that is 2 sigma. Next bonding orbital resulted due to 2px and psi2 group, labeled as 3 sigma. Then pi orbitals are there, 2py and 2pz. First time they are coming, so 1 pi. Afterwards, energetically, antibonding orbital resulted due to 2s and psi1 group, labeled as 4 sigma asterisk. And last orbital, antibonding orbital, resulted due to 2px orbital of beryllium and psi2 group, labeled as 5 sigma asterisk. And right side, pictorial presentation of all molecular orbitals is represented. Observe it neatly. At bottom, 2 sigma orbital is represented. Throughout that red region, positive phase is there. How many nodes are there? 0. Now see the 3 sigma orbital. There is a one gap. There is a one nodal plane possible. Left side one phase, right side other phase. So how many nodal planes are there, or how many nodes are there? One node. Now if you come to pi orbitals, as usual, how py and pz orbital they do possess one node. That one node will be there in each of the pi orbital. Then come to 4 sigma star orbital. How many nodes are there? Two nodes. For example, suppose if I consider two hydrogen positive, beryllium will be negative, hydrogen is positive. So 2 times the change in the wave function, change in the phases are there. So 2 nodal planes are there. For 3 sigma, only 1. For 4 sigma star, 2. Likewise, you will understand 5 sigma star has 3 nodes. And what is our rule? Increase in the number of nodes, increase will be the energy. Therefore, energy sequence is 2 sigma, 3 sigma, 4 sigma star and 5 sigma star. And about the pi interaction, which is weak interaction, or in case if it is a non-bonding, the energy levels will be as where the energies of the parent orbitals. So pi orbital energy is coming in between bonding and anti-bonding. So pictorial presentation of all molecular orbitals also is given there. Now let us see the other aspects of bond order and magnetic property. Yes, find bond order now. What is the magnetic property of BH2? Yes, what is the electronic configuration for BH2? 1 sigma 2, 2 sigma 2, 3 sigma 2, 1 pi 0, 4 sigma star 0, 5 sigma star 0. If I have to find the bond order, formula is number of electrons in bonding orbitals minus number of electrons in anti-bonding orbitals divided by 2. How many electrons are there in bonding orbitals? 2 electrons in 2 sigma and 2 electrons in 3 sigma, total 4 electrons. And in anti-bonding orbitals, no electron. So 4 minus 0 divided by 2. Answer is 2. 2 bonds are there. What about magnetism? Since there is no any unpaired electron, it is diamagnetic in nature, and that validates with experimental observation. As a homework, only one question is there. Why 2py and 2pz orbitals non-bonding in MO diagram of BH2 molecule? Write answer in comment box. Yes, let us discuss other polyatomic molecule, water, H2O, in next lecture. Interesting molecule.